Hi, and this is Dr. Habib Ahmed. Today I will be demonstrating how to analyze atomic force microscopy data using Nanoscope Analysis software. This powerful tool allows researchers to visualize two-dimensional and three-dimensional surface maps, characterize surface properties such as roughness and texture, and make precise nanoscale measurements. The software also supports advanced techniques such as force spectroscopy and phase imaging. These features make it essential for detailed surface analysis and material characterization in the fields of nanotechnology, material science, and biology. So, personally, I have performed atomic force microscopy like tons of times, but I'm only going to demonstrate selective results today. So I will show you the atomic force microscopy data analysis of non-miscut and miscut sapphire in both annealed and unannealed cases. I will show you the surface signatures for three nitride films such as indium nitride, gallium nitride, and aluminum nitride films. And I will also show you the surface morphology of aluminum deposited on top of aluminum nitride on sapphire substrates. Let us open the Nanoscope Analysis software, and I've got version 2.0 of the Nanoscope Analysis software. Let me full screen the software, and let me open the first file. So these are my folders. I'm gonna start with non-miscut sapphire, and let us first focus on unannealed non-miscut sapphire. So this is my sample A. I performed the measurements on a scale of 1 by 1 micrometer square, 5 by 5 micrometer square, and 500 by 500 nanometer square. Let me show you the result of 5 micrometer by 5 micrometers first. So I open this file, and now here is the surface of sapphire. Generally sapphire has got a really smooth surface, and today I'm going to show you for these samples how to use the plane fit operation and the flatten operation in order to smoothen the tilt or the curvature from the surface of your samples initially, and then how to determine the root mean square roughness of the surface of your samples. For comparison with other samples in literature, it's really crucial to determine the RMS roughness of your samples. Followed by how to measure different features, like for example the length and width and height of different features on your sample. Then I'm going to show you and how do I determine the length and width and height of different features on my sample by using this icon, section. Then I'm going to show you how to use this clean image icon in order to remove specks or spikes from my sample. Like for example, here you see this spike. Potentially you might have spikes on your samples because of measurement error. So you can actually remove these spikes using the clean image operation. And then I will show you how to export your files in 2-dimension and also in 3-dimension. I'm also going to show you how to change the scale over here. Like here you can see currently it's in the range of -1.7 nanometers to 1.9 nanometers. So I'm going to show you how to change the scale over different ranges, or how to make it an absolute scale as well. So let us start working on the unannealed sapphire substrate. Now I'm going to show you the annealing procedure for sapphire in a separate video, but currently let us just look at different surfaces. So first let us look at the RMS roughness of this sample. So I click on this icon, and my root mean square roughness for this sample is 0.393 nanometers. Anything for semiconductors, anything for these films which is below 1 nanometer, we call it sub-nanometer RMS roughness, is really good. So you can see that this film actually is really smooth. However, if you look at this sample in 3 dimension, for that purpose you click on this icon which says 3D image. So when you look at this image in 3 dimension, you find like it has got a lot of spikes over here. So smoothness generally is a relative terminology, and it's smooth, but still by annealing, for example, we can further improve the smoothness of this sample. Let me switch to 2 dimension once again, and you saw the RMS roughness of this sample was 0.393 nanometers. Now let me tell you the purpose of using the plane fit operation or the flatten operation. So this sample is smooth, but in a lot of cases you might have curvature on your sample, or you might have tilt on your sample, and because of that curvature or tilt, some areas are brighter as compared to other areas on your sample. So in order to remove the curvature or the tilt on your sample, we either use the plane fit operation, and here we can perform the plane fit in x direction, y direction, or in both x, y. Then we can use different orders, for example 0 to 6th order. And when we click on execute, so look at the shine on the sample, and now you see it has kind of changed. So after using the plane fit operation, and once again if we go back to roughness and look at the RMS roughness, it has improved from 0.393 to 0.348 nanometers. We can also perform the same operation. So this icon over here actually reverses whatever step we have taken previously. So it's an undo icon. So we reverse that, and now the color has changed to the previous state. Let us double check the RMS roughness. Once again it's 0.393 nanometers. So what I do is I can also use the flatten operation in order to or remove the tilt or the curvature from my sample. Similarly, you can like select from 0 to 6th order, and you can enter the number of histogram bins, etc. You click on execute, and it improves, it removes the curvature or tilt from your sample. And after that, if you click on the RMS roughness, now once again you see that now the RMS roughness is 0.344 nanometers. So this operation actually improved the RMS roughness because we removed the curvature from our sample. So the first thing was how to use the flatten operation and the plane fit operation, and then now you know how to measure the RMS roughness of your sample. Now we can also look at how to clean the image. Like for example, here you can see a spike right over here. So how do you remove the spike over here from this sample? So for that I'm gonna switch to 2D, and then I click on this clean image, okay, and then we create a box over here around this spike. There is a much bigger box. A smaller box should suffice. So I do that, and then we select spike cutoff. So it's 1 nanometer right now, and I don't know if this spike is above 1 nanometer. In order to check that, we can go to section, okay, and we draw a line around this spike to see the height of the spike. So as you can see, this spike is really tall. You can see the horizontal distance over here and the vertical distance. So you got two markers. One marker we can take it to the peak point, and another marker we can take it to the minimum value on this curve. And you see the vertical distance over here is going to change. You can see the vertical distance over here. So now it's 1.479 nanometers, and now it's 9.163 nanometers. So this spike is really tall. So we go back to the two-dimensional image view, and then I click on clean image once again and draw a box around this spike. And since it's greater than 1 nanometer, so 1 nanometer should suffice. But depending on the height of the spike, you can set it to 5 nanometers, 10 nanometers, whatever value suits you. And then we click on execute. 1 nanometer did not really work for me, so I'm gonna switch it to 0.5 and click on execute, and 0.5 worked. So now as you can see over here, the spike over here in the measurement has gone. So that's how you use the clean image operation on a surface on your sample. We go back to this view. Also, my color bar over here runs from -1.6 nanometers to 1.8 nanometers. Just left click on this color bar and it takes you to this window, and here you click on modify data scale, and here you can see like your data varies kind of in the range of 1.5 to 1.75. We can reset it to another value, for example 0.5, minus 0.5 to 0.5, to see how it looks. Actually in this case we are like skipping a lot of data, which is not good. So I'm gonna do like -1 nanometers to 1 nanometers. And in this work we are covering a lot of information by running the scale in the range of -1 nanometers to 1 nanometers. So then we click on OK, and now we see that my color bar now, the reference scale runs from -1 nanometers to 1 nanometers. There is also another trick that we can play. So color bar, if I click on this icon which says color bar scale relative to minimum data cursor, I click on this, and now your scale becomes absolute, running from 0 to 2 micrometers. So that's how you play around with the scale. We can also export our image in 2 dimension and also in 3 dimension. Before that, let me simultaneously open an annealed version of the same substrate. So I go to open, and by the way, we can open multiple files at the same time. So I go to non-maskered, and then I open the annealed sample, 5 micrometer by 5 micrometer. I click on this one. I have not flattened this one before, so I click on this one. Okay, so now in this case you can clearly see the effect of the tilt or curvature on this sample. So in order to remove the curvature from the sample, I go to flatten, and I click on flatten operation and click on execute. So now you can see the real image of your sample. So now you see that previously, here is my sample. We can just see points all over the place on top of the surface. But after annealing this sample, and once again I'm going to tell you about annealing of sapphire in a separate video, and I will show you the atomic force microscopy results for after the annealing as well. So after annealing, we get this beautiful step structure for this annealed sapphire substrate. And now let us check the RMS roughness of this annealed sapphire substrate. So I click on RMS roughness, and now you see the roughness has improved from approximately 0.35 for the unannealed sapphire substrate to approximately 0.0574 nanometers for the annealed sapphire substrate. So it's an approximate improvement of 7 times, or you can say, yeah, approximately 7 to 8 times improvement in the smoothness of the sample upon annealing. And also this kind of stepped surface morphology, it's called terracing step structure. So this kind of terracing step structure results in better growth of the following layers on top of the sapphire substrate. So we mostly grow aluminum nitride, gallium nitride, these kind of materials on top of sapphire substrate, and this kind of surface actually gives better results as compared to this kind of surface. So now you saw the RMS roughness comparison of these two samples. For a fair comparison, we need to keep the scale the same. So for example, let me change the scale in this case from 200 to like 500, minus 500 to 500 nanometers to see how it looks. And let us click on this option to see the absolute scale from 0 to 1 nanometers. Right now the unit is picometers. So now you can see the scale is running from 0 to 1 nanometers. Alright, and let us also change this scale from 0 to 1 nanometers to see how this one looks like. So now you can actually see the difference between these two samples, and you can see like a lot of white dots on this surface as compared to this one, as compared to the annealed one. Also, we can look at the three-dimensional images of these samples. So for three-dimensional view, we click on this icon and it gives you a three-dimensional view of this sample. We have control over the light intensity, for example, as well. So we click on this tab next to light intensity, and then the right arrow actually increases the light intensity on the surface. As you can see there, the light intensity has now improved. And similarly, we can decrease it at the same time as well. So now the light intensity has decreased. So we can play around with the light intensity. 90% should be enough. You can change the light rotation similarly as well. Similarly, you can change the background color from white to black. I like the white background more. And similarly, you can zoom the image. So I click on this tab and you can zoom it in, or you can zoom it out. You can select this figure and you can rotate it around as well. I like this view better. In fact, let me reduce it to like 1.45. So let me enter a value of 1.2. I like this better, but it's still smaller as compared to the scale. So 1.5 should be good. Cool. Similarly, you can also play around with the Z aspect ratio as well. So for example, I can change it from 0.2 to 1, and now you can see that this does not give me a good three-dimensional view of the surface of my sample. So let me reduce it now, take it to a value which gives me a better view of the surface. Let us rotate it around. I like this view better, so I'm gonna stick with it. You can further reduce the value, but this should be good enough. Similarly, you can also look at the 3D image of this unannealed sapphire substrate. So we click on 3D, and as you can see over here, you see a lot of white dots. Let us change the scale. Let us reverse it back to -1 to 1 nanometers, and click on OK. In 2D view, and then we look at the 3D view now once again. Okay, so here it is. You can see this. So the light intensity looks fine, but I want to play around with the Z-axis aspect ratio, this one. So I reduce it to like 0.05 should be good. Now this gives me a much better picture of the surface of my sample. I like this one more, so I'm gonna stick with this. So what you can do is you can actually export the two-dimensional image over here. In order to export a two-dimensional image, you need to click on this icon, and then here you got different options. TIFF looks good, so you can save the image in TIFF format or PNG format. TIFF looks good to me. You can also set the color quality of your image in dots per inch. So mostly for like different scientific journals, they might require you to submit your images in 300 dpi or 600 dpi. So based on that, you can actually set the quality of your image. Similarly, you can set the font size as well. Not in this one, but you can do it in 3 dimension. You also have the option to show the color bar off image or on image, or if you don't want the color bar at all. Similarly, you can show the data scale, show scan size bar off image or on image, show the data type. So the data type is over here. Right now we are looking at the height data type. You can also look at the amplitude or phase error on this sample as well. You can look at the amplitude or phase information of the sample over here. Okay, we're interested in this information more. So and then you can set the font size of the text and the font type over here as well. I'm gonna close this one. I'm okay with the current font size and font type, and then you click on export. So I export this file, and let us check it over here. Unannealed sample A 5 micrometers. Here is the exported image. In fact, it's I might have saved it somewhere else. So let me double check here. So I go to export and non-miscut. This is my unannealed sample, sample A, 5 micrometers, and then click on save. So it's actually this one, in which I've set the scale from 0 to 2 nanometers. So this is the exported image. Similarly, we can also export images in 3 dimension as well. I already performed the settings on my image, and here you click on export, and I export unannealed sample A, 5 micrometers, so the path is correct. I click, so in fact I will write 3D over here and click on save. So here is my exported image in 3 dimension, where the scale is running from 0 to 1 nanometers. You might wonder what is the width of each terrace and step over here. So in order to measure the widths, we click on section, and then you can run a line along the terrace and steps, and here we covered like 3 terraces. In order to measure the width of each one, we play around with the markers. So we are interested in the horizontal distance, and the horizontal distance is 0.560 micrometers. Similarly, we can check the step height as well. That would be vertical distance, and this is around 220 or 0.22 nanometers. So this is how you perform different measurements, and this is like one line, one measurement point. Its values are represented over here in the blue row, but you can include like other ones over here, and the second one is represented by the red one. Similarly, you can draw like vertical lines, tilted lines, etc. You can play around with it, and you can perform your measurements. Now I want to show you some other results. So now you know how to perform the measurements and how to export the files, but I just want to show you some other results. Like for example, let me show you the annealed 1 micrometer by 1 micrometer image. So we use the flatten operation, we execute it, and now you see the image, and you can see the terrace and step over here. You can see it's running from 0 to 1 micrometers. You can look at the 3-dimensional view of this as well, and you can set the aspect ratio to 0.05. So that gives like a beautiful view of this of the surface morphology of this sample. Similarly, now quickly I'm going to show you some other samples. So far I have shown you non-miscut sapphire samples. I also got some results for 3-degree miscut unannealed or plain sapphire. Here is a 5 micrometers version of this. So we perform the flatten operation, click on execute. You can look at the 3-dimensional view of this sample. It looks like this. And now let me show you the annealed R sapphire sample with a 3 degrees miscut. So you can see this beautiful tyrosine step structure across the entire surface of this sample. Let me also show you some other results. Our group at Georgia Tech, it's the Advanced Semiconductor Technology Facility, supervised by Dr. William Allen Doolittle, mostly works on 3 nitride materials, high power electronic and optoelectronic devices as well. So we perform the growth. In this group we perform like modeling and simulation, growth of samples, growth of thin films, for example, their characterization, so many different characterization schemes. We perform fabrication of devices and then testing of high power electronic and optoelectronic devices as well. I'm going to show you some representative 3 nitride films, which would be indium nitride film. This one was grown by my colleague Evan Andrew Clinton, and I performed the AFM analysis of this sample. So this actually is an indium nitride film. We can play around with the settings. Cool, this one looks better. So now the scale is running from 0 to 10 micrometers, and look at this beautiful image of indium nitride film. Growing this quality indium nitride film is not an easy job, and you can see the spiral helix mediated step flow surface morphology with interlocking steps, wound around the threading dislocations over here. These points actually represent the mixed threading dislocations. The spiral helix are generally associated with mixed threading dislocations in molecular beam epitaxy ground nitride films under metal rich conditions. But this surface actually is a signature of real high quality ground film, and growing indium nitride films is not easy because we have to keep the substrate temperature really low. These films are grown around 350 degrees C, and the dissociation temperature of indium nitride is 650 degrees C. So at high temperature you want to grow high quality films, where at the same times then the metal from your surface it's evaporating at the same time. So it's not easy to grow high quality indium nitride films. For high quality growth you also need relatively high temperature, and our group achieves high quality films at low growth temperature because we perform growths on using molecular beam epitaxy, but not just molecular beam epitaxy. We perform them using an advanced version of molecular beam epitaxy, which is called metal modulated epitaxy, in which the nitrogen flux is kept constant while modulating the metal fluxes using shuttering scheme. So if you are more interested about more metal modulated epitaxy, you can study some literature about it. And this technique was introduced by the wonderful Professor Dr. William Allen Doolittle. Let me and you can also look at the 3-dimensional view of this sample. So we can increase just playing around with this. Let's set it to 0.1. This gives me a much better representation of this sample. Let me show you some other samples as well. For example, gallium nitride and silicon. And because of their thermal and lattice mismatch, you will not see high quality films for gallium nitride grown on silicon substrates. It results in a three-dimensional growth, as is visible over here in this scenario as well. However, if you grow gallium nitride, if you perform home epitaxy of gallium nitride films, you can also achieve high quality films like this one. You can see spiral helix mediated step flow surface morphology for this gallium nitride film as well. And now you see like less number of spiral helix as compared to the previous, especially compared to the indium nitride films. You can see the step flow surface morphology over here in this region. I'm also going to show you a couple of other figures. For example, this one. I'm looking for a 5 micrometer by 5 micrometer image. I open this one. And I grade it under different growth conditions. And if I play around with, so like for example, let me set it in the range -3 to 3. Click OK, and now you can actually see like this is the spiral helix, and at the center of this you can kind of see the threading dislocation over here. So it gives us a particular hexagonal shape. And if you look at the RMS roughness of this sample, it's approximately 0.5 nanometers. So we have achieved sub-nanometer RMS roughness for these samples, which is a great achievement. These are high quality films. Let me also show you AFM image of the substrate. Click on execute. This is the substrate, and you can see a three-dimensional view of this as well, like step flow surface morphology. Similarly, this image, by the way, this is an actual image of when I was performing atomic force microscopy using Bruker Icon AFM tool. And here you can actually see my atomic force microscopy probe on the surface of my sample, and the laser is directed over here, kind of at the tip of the probe. Now let me show you some other films. MACS HVPE aluminum nitride film. Okay, perform the flattening, click on execute. So you can see this film in 3 dimensions. This is HVPE aluminum nitride film. You can see the pit over here. Over here you can see the pit, and I want to measure the, I want to draw a line across this pit. You can see the depth of this pit over here. Vertical distance is approximately 10.8 nanometers. The probe might not go like all the way across the pit, but gives us as much information as possible. Then I want to show you some other films, like for example, if we grow like a low quality film on top of the substrate, so you see a pitted surface of the aluminum nitride film under low quality growth conditions, and we can improve the growth conditions, and you can see the pitted surface morphology as well. Similarly, here is the surface morphology of a film grown on top of it's an aluminum nitride film grown on top of gallium nitride substrate, and this is a 1 micrometer by 1 micrometer image. I want to show you a 5 micrometer by 5 micrometer image. So let me open that one. And here is aluminum nitride grown at under high quality growth conditions, but on top of gallium nitride film. It's a heteroepitaxial growth, and we know that aluminum nitride has approximately a 4% lattice mismatch with gallium nitride. So aluminum nitride film with thickness greater than a couple of nanometers would actually result in either cracking if we are growing it under high crystalline growth conditions, or it's going to result in a high defect density under low quality growth conditions. So we see these cracks on top of the subsurface as well, and here is a 3-dimensional image. And I also performed scanning electron microscopy of these samples to give you a better idea about the cracks formation on the surface of this film. Similarly, let me show you another result, and it's aluminum film grown on top of nitrided sapphire substrate with a 1 nanometer intermediate aluminum nitride film, and you can see it has got high quality as well. In fact, you might find that we are kind of growing the best aluminum films on top of sapphire substrates in the world. So we got special recipes for that purpose. That concludes the session for today. So that's a wrap on our journey through the Nanoscope Analysis software. I hope this tutorial has given you the confidence to dive deeper into your AFM data and extract the insights you need. If you found this video helpful, don't forget to give it a thumbs up and share it with others who might benefit from it. Take care. Adios.